This is student page 45, lesson 8, module 3. The triangular numbers are the numbers that arise from arranging dots into triangular fingers as shown. I'm not going to lie to you, this is really a difficult problem. This is stage 1, 2, 3, 4, 5. One of the things I notice is that I go from 1 to 2, and let's see, we have 1 dot, we have 3 dots, we have 6 dots, we have 10 dots, and so what we do is we add the side to each one. But how can we make that an easy formula to figure out? To be quite honest, there isn't really a nice, simple, easy way. So what I'm going to do is I'm going to show you a little trick. What if I added 3 dots? Notice now that I have something that has the measurements 2 by 3. If I do the same thing to the next one, I'm going to go ahead and add 1, 2, 3, because I have 3 on the bottom, 2 to match this one, and then 1 to match this guy here. And now what I have is a 3 by 4. I'm going to go ahead and write this down here because I think that might be easier, and times 3 here. If I do it again, I'm just going to keep repeating this process. I'm going to add 1 here, hopefully make this even, 2, 3 here, and 4 here. If you notice, I've added exactly the same number of dots as I started with. This one's a 4 by 5. So let's think about this. What is 2 times 3? It is, and let me go ahead and give us another color. It is 6. This one is 12. This one is 20. And I bet you we could guess that this is going to be by 6, and it's going to be 30. So what's interesting is the whole thing. Now, can anybody see the relationship between the 10 and the 20, the 6 and the 12, the 3 and the 6, the 15 and the 30? What it looks like is we take the number of sides and multiply by the next number up. 100 times 101. But then that gives us a number that's too big. That's going to be 1,100. But that's twice as many dots as we should have. So we'll go ahead and we'll divide by 2 to come up with a final answer of 5,050. So how did we get that? Well, if you think about it, let's see. Actually, if I put the 2 under here, I think the answer is going to become obvious. The triangular number formula will be the number times the next number up divided by 2. How can you be sure your formula works? Try it. And that's the best thing to do. Let's try it. Let's see. If we do t of 4, we're going to find 4 times 5 over 2, that's 20 over 2, that's 10. Works. I like it. I could check one more. It might be a good idea. You always want to make sure you really do know what you're doing. Let's go T5. That would be 5 times 6 over 2, which would be 30 over 2 equals 15. We could keep doing more problems, but we can see that this works. Question 12. Create a graph of the sequence of the triangular numbers where n is a positive integer. So we're going to graph 1, 1, 2, 3, 3, 6, 4, 10, and 5, 15. Let me ask you a question. Arithmetic or geometric? This is almost the same question, but not quite. We're going to create the graph of the triangular area formula Tx, x equals x times the quantity x plus 1 over 2, where x is any positive real number. Notice that I've introduced some decimals, 0.2 and 4.8, which are giving me some decimal answers. I neglected to put in, I think I should put in 4 gives us, what did 4 give us? 4 gave us 4 times 5 over 2, which was 10. And let's go ahead and do 5, which is 5 times 6 over 2 equals 15. All I'm doing is taking the number, going 1 up, and then dividing by 2. All right, let's graph these points. All right, so this won't be quite as easy. Well, it'll start out easy. 1, 1, 2, 3, 3, 6. This one may become a little more obvious. I think really I spread the other curve out a little too much. 3.2 is at 6.72, which means 3.2 a little way out, but not quite 7. So we'll take that one. 4 is at 10. And 4.8, so almost 5, but not quite. 4.8 is 13.92. That's so close to 14 that we can practically call it 14, and 5 is 15. All right, so here's the thing. Now that we're allowing decimals or fractions, numbers that are not whole numbers, now so we can finish our graphing of these numbers by filling in the curve. And what this does is it tells us that basically any point on this blue line is going to be an answer to this question. How are the two graphs alike? That's the ones from 12 and 13. Well, they had the same shape and the whole number coordinates are the same. How are they different? In 12, we worked only with whole numbers. This meant that we couldn't graph in between the space. 13, we could use all the numbers, including fractions and decimals. What this implied is that we had to connect the points with a curve.